Hi everyone. In this video, we want to derive a second-order Taylor formula for scalar fields. When we first defined differentiability of a scalar field, we there defined a first-order Taylor formula for a scalar field. But now we want to extend that to a second-order Taylor formula in order to help us later on with the classification of critical or stationary points of a scalar field. So to begin, I want us to think back to the Taylor's versions of Taylor's theorem that we saw in Math 5610. So if you'll recall, if we take a function f, which is sufficiently smooth, that is simply to say that its derivatives of as many orders as you need exist, then we can write f of a plus h as f of a plus f prime of a times h plus f double prime of a over 2 factorial times h squared, so on and so on. Our nth term of our Taylor's formula will be the nth derivative of f evaluated at a divided by n factorial times h to the n, plus some remainder term or some sort of error term. One way we saw to deal with this remainder term was to simply define it as f prime of, the f n plus first derivative of f evaluated at some point c divided by n plus 1 factorial times h to the n plus 1 for some c between a and a plus h. Okay, so we saw ways of dealing with this sort of remainder term. This would then give us a exact equality. So for some particular c, this would then be an equality, or you could otherwise just characterize the error in the approximation. You could get rid of this term, write this as an approximation, and then define the error to be of this order. And so if we just want to limit ourselves to a second order approximation, and then what we can do is we just cut off, with the second term. So I've got f of a plus h is equal to f of a plus f prime of a times h, plus, now here again, if I'm doing an approximation, I'll just leave it as f double prime of a divided by 2 plus h squared, where then I would add on, some error term. Okay, and of course, this error term, I would probably here write it as h squared times e a h, where this EAH goes to 0 as h goes to 0. So I could just quantify the error in this way. Or alternatively, I could make this exact by simply replacing this a with some point between a and a plus h. So again, these are just, right now we're just recalling different forms of Taylor's theorem for a function of one variable and ways to express the error. So our goal is going to be to duplicate something like this for the case of a scalar field, which is a function of multiple variables, more than one variable. All right. So again, we've done this. We've got a first order Taylor formula. So for a differentiable scalar field, we could write a first order Taylor formula in this way. So we have f of a plus h is equal to f of a plus the gradient of f at a inner product with h plus norm of h times e of ah, okay? Where this e of ah goes to 0 as h goes to 0. But again, this h is now a vector, right? So this just falls out of the definition of differentiability. If your scalar field is differentiable, then there exists a linear operator, right, that goes here. And then we later showed that linear operator could be written in this way. It's the gradient of f at a inner product with h. So we've done this. We now really need to sort of hone in and figure out how to maybe express this in a more detailed way. So we want sort of the next term, that second order term, and then there'll still be some additional error, but we need to sort of add on to our formula here. All right. Now, in order to do this, we're going to need to use something called the Hessian matrix. Okay, so if f is a scalar field, and let's just go ahead and assume that it has continuous second order partial derivatives on some open set S, then we can define this Hessian matrix at a point A in the set S as the n by n matrix where, if I look at this, the entries along the diagonals are just the second partial derivatives with respect to each of the variables, right? So this is the second partial derivative with respect to x1, second partial derivative with respect to x2, so on and so on until we get to the second partial derivative with respect to xn. And then hiding in all these other entries are the mixed partial derivatives. Okay, so you'll notice that as we move along this first row, right? What we have here is the partial derivative of f with respect to x1 and x2. Okay, but notice that down here we have the same thing, although this is with respect to this is dx2 dx1, right? So slightly different order. Okay. But in general, right, we can describe this matrix in a slightly simpler way. So a more compact way of thinking about this, right, is that the Hessian matrix at A is the n by n matrix whose ijth entry is simply dij of f at A. Now, again, if we sort of switch back momentarily over here, right, you'll notice you have these mixed partials here, which if I'm dealing with continuous second order partial derivatives, by Clairaut's theorem, these mixed partials will be equal, okay? And in fact, by Clairaut's theorem, if all the second order partial derivatives are continuous, all of the mixed partials will be equal. So you get this nice property that by Clairaut's theorem, this Hessian matrix will be symmetric. Okay, and if you have, it's been a while since you took a linear algebra course, right? Symmetric simply means you have your diagonal entries, and then the ijth entry, so this would be the 1, 2 entry, is the same as the 2, 1 entry. So it's symmetric across this diagonal. Okay, so this entry and this entry would be equal to one another because, again, these are mixed partial derivatives, which by Clairaut's theorem must be equal to each other. Now, of course, this mixed partial will not be equal to this mixed partial, right? Because this is with respect to x1 and xn. This is with respect to x2 and x1. But mixed partials with respect to the same variables, regardless of the order, by Clairaut's theorem will be equal to each other. All right. So this Hessian matrix is a way of encapsulating all the second order partial derivative information into one matrix, right? So every second order partial derivative is somewhere in this Hessian matrix. So somehow this encapsulates all that second derivative information, and we're hopeful that as we try to expand our version of Taylor's theorem, this Hessian matrix, right, might pop up somehow. Now, it's also nice to have things organized in a matrix because, as we'll see, that allows us to use tools and results from linear algebra as part of our analysis. So just to make sure we're sort of clear on this, so let's just say we're dealing with a function of two variables, right? So the Hessian matrix here would simply be, so d12 of f, d1, sorry, that's a typo, that should be d11, sorry. That should be d11, this should also be d11, okay? So this should be d11 of f, d12 of f, d21 of f, and d22 of f. Of course, because of equality of mixed partials, this d21 will be the same as d12. So this is a symmetric matrix. Okay, and if we wanted to just sort of quickly work through an example, right? Take f of xy to be x cubed minus 3xy plus y cubed. You can go through, I'm not going to spend the time if you want to sort of pause it and work it out, right? But you should be able to compute each of these partial derivatives, and then you can plug them in here to come up with the Hessian matrix for this particular function f. Now, I will note that when we're working with a particular function, sometimes we might write h sub f to denote that it's like a particular function we're taking the Hessian of. So this is the Hessian of this particular function f. When we're dealing with it in the abstract, to save on notation a bit, as long as it's clear, I tend to just write h But if we ever needed, say, the Hessian matrix for multiple functions, say f and g, I might write h sub f and h sub g to help differentiate those two. So great. That's the Hessian matrix. Now, why it's sort of seemingly out of the blue that I'm introducing this Hessian matrix, okay? But as you can sort of see here, it's going to pop up here in our second order Taylor formula. So this is the main result for this video. Let's take some time to understand what this theorem is saying, and then we will work through a proof. So I want to suppose I have f as a scalar field with continuous second order partial derivatives, and they are defined on some n ball B of A. So that's some little ball centered at the point A. Okay, so in some neighborhood of A, all of my second order partial derivatives are continuous. Okay. Now again, note that this is going to allow us to apply Clairaut's theorem. We're going to have equality of mixed partials. This is nice. It's a nicely behaved function f, at least near A. Okay. So in that case, for all y in Rn, such that A plus, and this is I'm off to a bad start. This should be a lowercase y, such that A plus lowercase y lies in BA. Okay. So the idea is I'm in my domain space here. Here's A. Okay. For all y, such that when I add y to A, okay, so that's going to give me this point A plus y. As long as that point lies inside this ball, right? It has some radius, but this whole thing is just B of A. So for all y, such that A plus lowercase y lies in B of A, we have f of A plus y. So notice this is going to be our second order Taylor formula. So f of A plus y is equal to f of A plus the gradient of f of A dotted with y. So if I ignore this, if I ignore all of this stuff sitting over here, this is looking like the first order Taylor formula, which is good. Plus, now if I look here, okay, I have 1/2. That seems reasonable from other things I've seen. And then I have y times h of A plus cy times y transpose for some c between 0 and 1. So let's not worry about the or equivalently part yet. Let's take this part first. Okay. One way to think about this is A plus cy for c between 0 and 1 really just means, right? I'm looking at some point here, right? That's between A and A plus y. So one way to think about this is sort of you think about taking your scalar field f and you restrict it to this segment between A and A plus y. Okay. And this is actually how the proof will work. You restrict it there, and then this is really just now some point between A and A plus y. This is really starting to look like that Taylor's theorem that we saw earlier, right, where I had like a f double prime of some point c that was between A and A plus h. Well, now I'm just writing A plus cy to represent some point on the line segment between A and A plus y. Okay. Now, over here, this quantity, like if we think about what all these quantities are, right, f is a scalar field. So f of A plus y is a scalar, f of A is a scalar. The gradient of f of A is a vector, but I'm going to take inner product with y, so that's going to give me a scalar. So this thing ought to be a scalar, right? Because I want my output to be a scalar. I've got scalar plus this better be a scalar. Now, this is where it's important to understand that Apostles' book thinks of vectors as row vectors, okay? So y is a row vector, h is an n by n matrix, and y transpose is then just the column vector with the same entries from y, right? So if you remember a little bit of linear algebra, this is a 1 row by n columns and n times n matrix, and then an n by 1 vector. All our inner dimensions match, so this matrix multiplication is well defined. And at the end of the day, we end up with a 1 by 1 matrix. It's really just a scalar, right? So this y times h times y transpose, this really gives us back just a scalar. Now, the other way we can express this, so this is where the or equivalently part comes in, is to say, well, I really would like this to be at A. That's the point I'm sort of interested in doing the Taylor expansion around. So I'd like this to be at A, but then that's not going to give me the exactness I want. So then I'd like to be able to quantify my error. And so what this term does is gives you a way of quantifying your error. So you can actually do this at A, but now the error is the norm of y squared times e of ay, where e of ay goes to 0 as h goes to 0. Now, don't get confused. This e of ay is not the same e of ay from the first order Taylor formula, right? But it's behaving in a very similar way. It's just some error term. And the fact that you actually have a norm of y squared here, right, means that this whole error term is going to 0 very quickly, right? Because as y goes to 0, this is going to 0 like in a quadratic fashion, and the rest of this is still going to 0. So it's going to 0 a little bit faster even than norm of y squared. All right. If you actually study more computational numerical type things, the analysis of these error terms actually becomes a very important deal in understanding the error in certain types of numerical approximations. All right, so we want to be able to prove this. So let's see if we can step through this. Now, something we've seen several times now and we'll continue to see right now even, is that we want a second order Taylor formula for a scalar field. We have one for real valued functions of a single variable. Maybe I can find some way to use that, okay? So let's start. Okay. Let's let y be a fixed vector. And let's choose it such that a plus y is in my ball. Oops. Centered at A. Okay. Also, it's important to note that as soon as A and A plus y are in my ball, A plus cy must be in my ball for every c value between 0 and 1. So any segment that with endpoints A and A plus y must also be in the ball. That's actually sort of interesting geometric thing. It's maybe not so interesting in Rn, but it turns out to be very important in other spaces. All right, so we're going to define a function g of u to be f of a plus uy for u values between -1 and 1. Okay. Now, notice that this function g of u, what kind of function is it? U is a scalar. So this is a function of a scalar value. It's a function of a single variable. And it outputs what? Well, it outputs values of f, which are r. So g is a function from some subset of r into r. Okay? It's a single variable function. So we can treat this in the way we treat pretty much any other type of function from r to r. We can use lots of those results from 5610. All right. So what we want to do then is we want to understand, I really want to understand this quantity. So I'm going to write it in this way. I want to look at f of a plus y minus f of a. So really, if you think about proving that Taylor's formula, I'm going to subtract the f of a term over. Okay. So what I'd like to do eventually is show this is equal to 1/2 y h y transpose, where that h is evaluated at a plus cy. Okay. So, but if I express this in terms of g, f of ay, that's just g of 1. F of a, that's just g of 0. Okay. And now I can apply Taylor's theorem here. So if I was to just use this, the normal version of Taylor's theorem, I'd say, okay, G of 1 is equal to G of 0 plus G prime of 0 times 1 minus 0, but that's just 1, plus 1 half G double prime of 0 times 1 minus 0 squared, but again, that's just 1. So I'm subtracting the G of 0 over, and so what I get is that this is equal to G prime of 0 plus 1 half G double prime of, oh, sorry. If I want this to be equal, right, this is C for some C between 0 and 1. So this should be C here. Okay. So now what I need to understand is I need to understand what on earth these values are, right? Okay. So let's do a little computation here. So let's first try to take a derivative of G with respect to U. That's the only variable there. Okay. So that's going to be the derivative with respect to U of this function f. Now remember, f is a function of multiple variables. Okay. So I have to apply the chain rule. I need to take a derivative with respect to each variable. Okay. So I'm going to take a derivative with respect to the first variable and then take a derivative of the U stuff. Okay. So if I think about what's going on here, okay, I could express this as f of like a1 plus uy1, comma, a2 plus uy2, all the way up to an plus uyn. So to take a derivative with respect to u, I would first take a derivative with respect to the first variable times y1, okay, plus derivative of this whole thing with respect to the second variable times y2. So one way to express that is to say I'm going to take the sum j equals 1 up to n. I'm going to take the derivative with respect to the jth variable of f evaluated at this point. I'm going to go back to expressing these in vector notation, times whichever of the, if I took it with respect to the first variable, then I'm going to get out y1. With respect to the second variable, I'll get out y2. So I'll just get times yj. Now, if I look at this, this is actually the same thing as saying this is the gradient of f at a plus uy in a product with y. So here we have sort of a chain rule. We're just applying a chain rule here to find the derivative g prime of u. Okay. All right. So if I want g prime of 0, right, because that's what I'm going to want up here, g prime of 0, if I plug in u as 0, this will just be gradient of f at a in a product with y. Okay, perfect. I sort of expect to see that in this formula, right? So that's good. That's what I get there. Now the question is, what do I get if I want the second derivative? So if I want the second derivative of g with respect to u, well, I'm sort of going to do the same thing, right? I'm going to come here and I'm going to take a derivative of, this is now the thing I'm taking a derivative of. Okay, so I'm going to come here, I'm going to take a derivative with respect to each of the variables, right? And then as I take a derivative with respect to each of those variables, what's going to come out is going to be whichever particular y term I'm in. So I'm going to take a derivative with respect to each variable of this function. Use a scalar. And when I do that, right, So I'm going to take this derivative, but then the chain rule is going to pop out one of the y components. And when I'm taking the ith derivative, that's going to pop out yi. So what I end up with at the end of the day is actually a sum I equals 1 to n, sum j equals 1 to n of d ij, because now I'm going to take the ith derivative of the jth derivative. Okay, so I get a dij of f of a plus u y times y j times yi. Now, if I take a little care, I can actually express this as a matrix multiplication or a matrix vector multiplication. So this is, in fact, y times h of a plus uy times y transpose. Okay. And so all of this tells me that, well, let's even go ahead and take it a step further. We want to write 1/2 g double prime of c. That's going to be 1/2 y h of a plus cy times y transpose. So now to complete my proof, all I need to do is go back up here and plug in exactly what I had. So if I erase these derivative calculations that I had to do, which are really, in a lot of ways, they're the hard part here, right? Being careful about how to express these derivatives. But once you do that, right, we're really just applying Taylor's formula for a function of a single variable. So we're taking this scalar field that has a higher dimensional domain, we're restricting it to a particular line segment, which gives us, we can then express as a function of a single variable by parameterizing that line segment. And then just some careful calculation of the derivatives gives us the result we want. So we just saw then that g prime of 0 is just the gradient of f at a inner product with y. And 1/2 g double prime of c is 1/2 y h of a plus cy times y transpose. Okay? And so if I look at what I have here, right, I have exactly what I want. And this holds for some c in 0, 1. Okay. Now, that's the proof of sort of that first formulation of the second order Taylor formula. What about that second formulation? Well, I'm actually not going to do, I'm not going to prove that super in depth, but the idea is you define actually that error function. You just say let e of a y be equal to y times h of a plus cy minus h of a times y transpose divided by 2 norm of y squared. If you plug that into that formula, you actually get that it reduces to the first formula. And then all that's really left to show is you need to show that this piece, you need to show that this e of a y goes to 0 as y goes to 0. And so you need to do a little analysis and estimation. The book does this on page 309 and 310. You can see that, but it's not particularly difficult. I don't want to focus on that too much. But you just need to do a little analysis there to show that this error function does behave as we expect, and it does. All right, so that gives us the second order Taylor approximation. Now, a very reasonable question to ask is, why are we working so hard for this second order Taylor approximation? Well, I've already sort of mentioned, although it's not the reason we will use it so much, that Taylor expansions are really important for computational and numerical algorithms for approximating solutions to things. So it's a good reason to study them in general. They are also very useful in helping us to classify critical points or stationary points of different types of functions, in this case of scalar fields of multiple variables. Now, we will actually do that in the next video, but I want to start by looking ahead just a little bit. Okay, so that term that we saw, this y h of a y transpose, it's actually a special type of form that pops up. You can also express this, for example, as the inner product of y with h of y. So that's, I guess that would be like a transpose because you need that. So this is really an inner product that's going on here. So you can study these things called quadratic forms. So this is the quadratic form associated with this Hessian matrix. And this is, again, it's just that second order term that pops up. Quadratic forms, there's a whole, I mean, you can study these much more in depth than we're going to. We want to use some results about these quadratic forms in order to inform sort of our understanding of this Taylor's formula in certain situations. So this quadratic form, this takes as an input a vector in Rn, right? And it spits out a scalar, okay? Now, if I go back to that Taylor formula, right? Let me actually skip ahead real quick. So if I sort of go to this Taylor formula and look at this, if I happen to be at a critical point, right, or a stationary point, that's going to be where all of my derivatives are zero. All of my partial derivatives are zero. All of my directional derivatives are zero. And so this term is going to disappear. Okay, that term will be zero. So what I'll have is that the difference f of a plus y minus f of a, and one way to think of this difference is it's the difference between your function values at a, and if the norm of y is small, this is the difference between f of a and a nearby point, okay? So that difference is 1/2 y h of a y transpose plus this term, this error term, that if you think about it, if y is small, if I'm thinking about a nearby point, if y is small, this is going to be super small, right? Because if y is already small, if it's less than 1, then y squared will be even less than the norm of y, okay? And this is also going to 0. So for y close by, this ought to be as small. I ought to be able to make this as small as I like. This quantity, its sign should really tell me what the sign of this is going to be. Because if this is negative, who cares if this is positive? It's going to be so small that it's not going to be enough to change the sign of this. Okay. Now, why do we care about the sign of this? Well, if I want to know whether I'm at a maximum or minimum, what do I want to know? I want to know the difference between between f of a and f of a point near a plus y. Okay. So we really need to understand the sign of this and how it depends on this particular Hessian matrix. Okay, so we want to know how this matrix H affects the sign of this quadratic form that comes from H. All right. Well, it turns out, and this is sort of the last thing I'll show you, this is really a linear algebra result. We're not going to prove it, but we'll make some use of it, and we'll restart with this in the next video. But if you know something about the eigenvalues of your matrix, that can actually tell you something about the sign of your quadratic form. So we'll conclude with this theorem. So imagine you have an n by n real symmetric matrix. Notice that our Hessian satisfies all of those things. It is n by n, it's real valued, and because we're only working right now in the situation where Clairaut's theorem applies, that Hessian matrix is symmetric. So if you have an n by n real symmetric matrix A, and you take the quadratic form that's generated by A, so that's YA, Y transpose, then you have the following result. The quadratic form Q of Y will be positive for all non-zero vectors Y if and only if all of the eigenvalues of A are positive. And the quadratic form will be negative for all vectors Y not equal to 0 if and only if all the eigenvalues of A are negative. So what this does is this theorem gives me a connection between information about this matrix A and the sign of the quadratic form. Okay. Now, we want to do a little more work because it's computing eigenvalues of a matrix. I mean, by hand, that's a little difficult, but I mean, it's also difficult computationally. We'd like some slightly easier ways of dealing with this. So what we will see in the next video is that by using some simpler information about matrices, and in particular, if we're, say, just looking at a function from R2 into R, we can actually do more to classify critical points of these functions as either local maxima, local minima, or a special type of other option that we get in multiple dimensions, which is a saddle point. So we'll conclude this video here, and we will complete the classification of critical points in the next video.